Okay, so now we want to talk about acceleration from more of a calculus standpoint, okay? And we're going to define acceleration exactly the same way we did before, okay? Your average acceleration is exactly the same as your average velocity was, okay? It's just the change in velocity over the change in time, just like the average velocity was change in position over change in time. But your instantaneous acceleration, on the other hand, okay, is your change in velocity over change in time in the limit that your change in time, or delta t, goes to 0. And that turns into the derivative. So your acceleration is just dv dt. But since your velocity is dx dt, your acceleration is also d squared x dt squared. So if you have a position versus time function, or position as a function of time, and you need to get the acceleration, you need to take the second derivative, okay? If you're given a velocity function, then all you need to do is take the first derivative, all right? So, as an example, let's say that we have a particle and it is constrained to move according to this position versus time function over this time interval right here, okay? And we have a plot of the function right here, so it's going to start at the origin and it's going to move downward, and then it will grow upward over there, all right? Now there's one more interesting question that we could ask, okay, on top of these, all right? And I'll discuss that a little bit as we get further in the video. But for the moment, let's restrict ourselves to finding our velocity, finding our acceleration, and finding when the velocity is 0. That's a rather interesting question, okay? So let's start there. So to find the velocity, all we're going to do is take the derivative, right? Because remember that v is equal to dx dt. So, and this is going to give my velocity as a function of time. So v as a function of time is going to be 6 t squared minus 3, okay? So there's my velocity as a function of time. What about my acceleration? Well, remember, acceleration is dv dt or d squared x dt, all right? And of course, in this situation, either one is going to get you to the promised land, so quote unquote, all right? So if I take the derivative of my velocity function, I'm going to get 12.0 t, all right? Or we don't need parentheses here, 12.0 t. So at any point in time, I can find the acceleration at any point in time, all right? At any point in time. And we may do that here in just a moment. But before we go there, let's look at C, okay? Find the time value when v equals 0, when my velocity equals 0. So since my velocity is the derivative of my position versus time, that means that the velocity is going to be 0 at a local maximum or minimum, okay? And it turns out that with our graph here, we only have one local minimum, and that occurs right here, right? Recall that the derivative is a slope, and so your minimum or maximum occur where your slopes are 0. And so if I draw a line tangent to my curve here at that point, I can see that my slope of the line tangent to the curve at that point is 0. So it is this time right here. It is that point in time that I want to find, okay? So what we can do is we set our velocity function equal to 0 and solve. So to do so, okay? So we have this, and if I take the square root, I'm going to say approximately because the square root of 1/2 is irrational, it goes on, okay? But to 3 significant digits, this is quite accurate, okay? So it's approximately 0.7 seconds is when the velocity is 0, and that's you can, my sketch isn't too off, right? That's pretty good. Now, one more interesting question we could ask is, what is the acceleration at this point in time? Okay, what is the acceleration at that point in time? And if I want to find what the acceleration at that point in time is, all we have to do is plug in for 0.7 here. And again, I should say something about units, okay? We're going to assume that all of our units are appropriate such that this 2.0 has the appropriate units to come out to meters. So this would be meters per cubic seconds, and this would be meters per second, okay? So if this is meters per cubic second, then seconds and per cubic seconds will turn into meters per second squared. So this will come out to have the units of acceleration. And so I'm not going to worry about calculating the number. You can calculate that number, whatever it would be, okay? But that would be what the acceleration is right at this point in time. Now, one thing to note, okay? Our acceleration is always going to be positive. Our acceleration is always going to be positive. We're restricting our values to between 0 and 2 seconds. And so if I plug in 0 and 2 seconds down here, I will always get a positive number. So I'm constantly accelerating. I'm not decelerating at all. But you might be tempted to think that I'm decelerating here since I'm moving in the negative x direction, right? I'm moving in the negative x direction, and then at this point I kind of turn and then I start moving in the positive direction again, okay? But what is physically happening, even though I'm moving in the negative direction, I'm actually slowing down, okay? So I'm slowing down in the negative direction, and then I'm getting accelerating in the positive direction. So this would be something like if I define a coordinate system like this, and I make this the origin, and I let this be positive x, let this be negative x. This might be something where my object initially starts moving in this direction, in the negative direction, but it's constantly slowing down and then moves back in this direction, right? So if I slow down in this direction, right, I'm moving and then I slow down, that means I'm accelerating in the opposite direction. Anytime I decelerate, that means I'm accelerating in the opposite direction. So since I'm slowing down, that means I'm accelerating this way, and then I get taken back and accelerate uniformly again. Well, not uniformly, but according to 12.0 times t, right? So I'm slowing down and I turn around and then I move off in the other direction, okay? And that's exactly what we see happening here. My acceleration can always be positive even if my instantaneous positions or velocities are negative, okay? So you can have negative accelerations, but you don't have to. So just because I might be moving in the negative direction here does not mean that my acceleration is negative. All right, I just wanted to make that point clear. Hopefully that wasn't too confusing. But that is one of the calculus ways that you can use positions and velocity functions to find accelerations.